Our final topic in Chapter 4 is solution stoichiometry. So we'll utilize the molarity formula as a conversion factor. So here's a basic example. If we react magnesium solid with hydrochloric acid, we form hydrogen gas and magnesium chloride, which I'm sure we've all seen. So the question wants us to determine the volume of the hydrochloric acid required to react with the 24.3 grams of magnesium. So in good stoichiometry practice, write our amounts underneath the values in the balanced equation. Volume, we'll do liters, and it's 6.0 molar. So we start with our 24.3 grams of magnesium. Obviously we need to get the moles so we can convert to the hydrochloric acid. So we have 24.3 grams of magnesium to 1 mole of magnesium. Balanced equation has 1 mole of magnesium reacting with 2 moles of HCl. And according to our molarity, there are 6.0 moles of HCl for every 1 liter of the solution. This gives us a volume of 0.33 liters. And yeah, so our molarity is only 2 significant figures, so that would only have 2. Right, so we have, basically we're just gaining this conversion factor here that allows us to get from liters to moles or moles to liters of an aqueous solution. Now, the application of this, oftentimes we will do titrations in which we are adding a titrant to another reactant. So the titrant is the solution that is in the burette here. And we would be titrating that into another solution below and observing the reaction. In a simple acid-base titration, we would continue to add in this case, the sodium hydroxide, the base, to the unknown acid in the solution below until an indicator had changed color, indicating that we had reached the end point. At which time we would know the volume of the one reactant that's inside the burette. We could figure out how many moles of that, use the balanced equation, and figure out how many moles of our acid were in the flask at the bottom. And then, of course, we would have different calculations we could do with this. So here's some sample data. If we use 20 milliliters of acid, and the acid is an unknown concentration, our NaOH molarity is 1.0 molar. Our initial burette reading is 1.24 milliliters, and our final burette reading is 41.24 milliliters. We would know that we used a total of 40.00 milliliters of the NaOH, and that the concentration of that was 1.0 molar. We need to figure out the molarity of this solution, and we do know that we had 20.00 milliliters of that we started with. So to figure out the molarity, we would have the number of moles of HCl divided by the volume, which would be 0.02000 liters. So we just need to figure out the number of moles of HCl. We're going to take our volume of NaOH that we titrated in to get to our end point. We're going to use the molarity. So we have 1 liter or 1,000 milliliters is equivalent to 1.0 moles of NaOH. Common strong acid, strong base reaction. For every 1 mole of NaOH, we must have had 1 mole of HCl. So we would see that we must have had 0.040 moles of HCl. So if we go back up to our equation, I'm going to work horizontally here. 0.040 moles of HCl, 0.02000 liters gives us a molarity of 2.0 molar for our unknown acid. Now this is assuming that the indicator changed color at the right point, and we'll talk more about the indicator colors later on in the year when we get to talking about strong and weak acids and bases. So here's a review of the acid analysis by titration. First you would have a known volume of an unknown acid, and it's titrated with a base of known concentration. The indicator is added so that the endpoint can be identified. In the lab you would measure the initial and final burette readings, record those in your lab journal. You'd use these to determine the volume and ultimate number of moles of base that were required. Again, we're using stoichiometry to figure out the number of moles of acid. And then finally, once we had the number of moles of acid, we could then use that to figure out the concentration of the original acid solution.